A buffer solution is another type of a common ion effect. What it does, it resists large changes in pH when small amounts of strong acids and bases are added. So you could think of buffer solution as Le Chatelier's principle. This is what a buffer solution does conceptually. We have a weak acid and it partially ionizes or dissociates into H plus AQ and C2H3O2 minus AQ. We're going to add a strong acid such as HCl. When I add a strong acid, we already know that it breaks down 100% into H plus and Cl minus. Since it breaks down into H plus and Cl minus, it increases the concentration of the H plus ion. According to Le Chatelier's principle, when a stress is added, the equilibrium is going to shift to reduce the added stress. So this reaction is going to shift to the reactant side to decrease the added stress or the increase of H plus. To explain this in buffer terminology, if I add HCl, the H plus concentration increases, which means that the pH is lower or it's more acidic. So what the buffer solution does, it resists the change in pH by shifting the equilibrium to the reactant side. When the equilibrium is shifted to the reactant side, the H plus concentration decreases, increasing the pH of the solution. pH measures H plus concentration. The higher the H plus concentration, the lower the pH, because lower pH is more acidic. That means higher the pH, there's less H plus concentration, so it's least acidic or more basic. If I add a strong base such as NaOH, it also dissociates into its ions Na plus and OH minus. OH minus is added to the equation. The OH will combine with the H plus to create water, therefore removing H plus ions. So my H plus ions decrease. According to Le Chatelier's, it's going to relieve that stress by shifting towards the removal because it wants to produce more. So it's going to shift to the product side to increase the H plus concentration. So in buffer terminology, H plus was removed to produce H2O. The pH increased or became more basic because there's less H plus ions. The equilibrium will shift to the product side to increase the H plus concentration, lowering the pH, making it more acidic, resisting the change. So the buffer solutions also apply to weak bases. Ammonia is an example of a weak base. If you do not know how to write a weak base dissociation, always react it with water. Water will behave like a bronzene laurate acid, and the weak base will behave like a bronzene laurate base. The acid will donate one hydrogen, so NH3 will become NH4 plus, and the H2O will become OH minus, and these become conjugate pairs. Please remember, a weak acid, when it dissociates, must have a H plus on the product side. A weak base, when it dissociates, must have a OH minus on the product side. So if I add HCl, again, it's a strong acid, so it's going to break into H plus and Cl minus. If I add this to the reaction, the H plus will combine with OH minus to produce H2O, therefore removing the OH minus ion. According to Le Chatelier's principle, the equilibrium will shift towards the removal to increase the concentration that was removed. In Buffer's terminology, when the OH is removed, there is less OH minus, so it's becoming more acidic. To prevent solution becoming more acidic, the equilibrium is going to shift to the product side to increase the production of OH minus to make it more basic. If NaOH is added, it's going to dissociate into Na plus and OH minus because the added OH minus will increase the OH minus concentration. And according to Le Chatelier's, if something is added, it's going to remove the stress by shifting to the opposite side. In terms of buffer solution, as more OH is added, the pH increases. It's becoming more basic because there's more OH minus ions. To resist the change, the equilibrium is going to shift to the left, decreasing the OH minus concentration, making it more acidic. There are two main types of buffer solution. An acid buffer, it will contain a weak acid and a conjugate base. Remember, conjugate pairs differ by one H or one hydrogen, or a base buffer which contains a weak base and a conjugate acid. So let's look at this first problem. It says calculate H3O+. H3O+, if you remember, is the hydronium ion. It is another way of writing H+. That is 0.10 molar in HF and 0.20 molar in NaF solution. Also calculate the percent dissociation. The Ka is provided as 7.2 times 10 to the negative fourth. Since Ka is provided, we are going to start with an acid. The acid provided is hydrofluoric acid. We're going to dissociate that into its ions. Remember, weak acids do not dissociate 100%. H plus and F minus, AQ. The H plus is the same thing as hydronium ion. You get H3O plus if you react HF with water. So here, the HF is your acid or bronzed lauric acid. Your water is my bronzed lauric base. The HF will give a hydrogen to the water because the acids give. This is how we get H3O plus, the hydronium ion, and we have F minus by itself. This top equation and the bottom equation are the same thing. You could use either or. But for acids, it's easier to just break the acid into H plus and its ion form. We are going to look for H3O plus, so we must create an ice table because it's at equilibrium. Initial concentration of HF is 0.10 molar. H plus is 0, and the F minus NaF is given. This is a common ion effect. So this breaks down into Na plus and F minus, so this becomes 0.20 molar. Since the equation is 1 to 1 to 1, my change is going to be minus X for the reactant. Products are going to be plus X plus X. My equilibrium, I add the IC, so this is going to be 0.10 molar minus X, X, 0.20 molar plus X. Now I'm going to write my equilibrium equation. Equilibrium Ka is going to be products over reactants, which is H plus F minus over HF. Now I'm going to plug in my values. H plus is X, F minus is 0.20 molar plus X divided by 0.10 molar minus X. This is equal to Ka, which was given as 7.2 times 10 to the negative fourth. So I'm going to assume the 5% rule. Therefore, this approaches 0, this approaches 0. Solving for X, X is equal to 3.6 times 10 to the negative fourth molar. This is equal to the H plus concentration. To determine the percent ionized is going to be the H plus concentration divided by the initial concentration, which is HF. times 100. This is equal to 3.6 times 10 to the negative fourth molar divided by 0.10 molar times 100 equals to 0.36%. The 5% rule is valid because this is not even equal to 1%. Pause the video, solve this problem on your own, and then check your answer. So calculate pH of a solution that is 0.5 molar HAC, which is AC stands for acetate, and 0.5 molar NaAC. Ka is 1.8 times 10 to the negative fifth. So this is just a basic common ion effect. So we're going to take our acid and we're going to dissociate it because Ka is given. So H plus AQ plus AC AQ. Ice table. Initial concentration of HAC is 0.50 molar. There is 0 H plus initially. Because this is a common ion, anything with Na usually breaks into Na plus and AC minus. My initial concentration of AC is no longer 0, but 0.5. It is 1 to 1 to 1. It's going to be minus X, X, X. And I'm going to add IC to get my equilibrium. Now I'm going to write my equilibrium equation. So Ka is going to be products over reactants. So this is going to be H plus times AC over HAC, plugging in X times 0.50 molar plus X over 0.50 molar minus X. This is equal to Ka, which is 1.8 times 10 to the negative fifth. Again, I'm going to assume the 5% rule, so these x's are going to be really small, approaching 0. Calculating for x, x just becomes 1.8 times 10 to the negative fifth because these cancel out. So the 5% rule, A minus over HA times 100. So this is 1.8 times 10 to the negative fifth over 0.50 molar times 100. This equals to 0.0036%, which is much lesser than 5%. So the 5% rule is valid here. Now we have to calculate for pH. pH is equal to negative log of H plus ion. This is negative log of 1.8 times 10 to the negative fifth molar because X is equal to the equilibrium concentration of H plus here. So this becomes 4.7447. Sig figs, there are 2, so I need 2 in my answer, so it's right here. 4.74. Sig figs for pH start after the decimal. Pause the video, solve this problem on your own, and then check your answer. So on this one, we are calculating the pH of a solution formed when 500 ml of a 0.1 weak acid is mixed with 500 ml of a 0.2 solution of its salt NaX. So before we even start the ice table, we need to figure out what is my initial concentration. My initial concentration is not 0.1 or 0.2 respectively for the compounds because we are not using 1 liter, we are using a mixture of 500 ml. So that means the volume is going to be additive. In order to calculate this, the first thing I need to do is calculate the moles present of the weak acid in 0.1 molar and the number of moles present in 0.2 molar of NaX using dimensional analysis. So 500 milliliters of HX, there's 1000 ml in 1 liter, and 1 liter has 0.10 has moles of HX. This is equal to 0.05 moles of HX. Same thing goes for the salt. 500 mLs of NaX. We need to convert it into liters. 1 liter has 0.20 moles of NaX. This is equal to 0.10 moles of NaX. So here the volumes are additive, so the new molarity of HX is going to equal to the moles over the volume of solution. The moles calculated is 0.05 moles of HX divided by 500 ml plus 500 ml converted into liters. And so the concentration of HX 0.050 molar HX. So the molarity of NaX is the same thing. It's going to be 0.10 moles of NaX over the total, which is 500 milliliters plus 500 milliliters over 1 liter over 1000 mLs. This equals to 0.10 molar NaX. Understand why we're doing this. Without doing this step, your process is incorrect. In this problem, we have to calculate the new concentration of HX and NaX because the volumes are additive. Since we are not mixing 1 liter of each solution, but only half the number of moles per solution is going to be half. Now we can write our equilibrium equation. So my acid is HX. This is going to dissociate into H plus AQ plus X minus AQ. Using my ICE table, the values I use are when the volumes are additive. HX 0.050 molar. I have no H plus ions. Since my NaX is a salt that dissociates, my X minus is 0.10 molar. This is a 1 to 1 to 1, so this is minus X, X, X. Equilibrium is the addition of IC. So now I write my Ka equation, which is products over reactants, which is H plus X minus over HX. This is X, substituting in 0.10 molar plus X divided by 0.050 molar minus X. This is equal to 4 times 10 to the negative fifth. I'm going to assume the 5% rule. So these x's approach 0. So x, after calculation, becomes 2.0 times 10 to the negative fifth molar. This is the concentration of H plus at equilibrium. Percent dissociation is x over hx times 100. This is 2.0 times 10 to the negative fifth molar divided by 0.050 molar times 100. This equals to 0.04%. So the 5% rule is valid. To calculate the pH, pH is equal to negative log H plus, which is equal to negative log 2.0 times 10 to the negative fifth molar. This is equal to 4.6989. Since my answer has 2 sig figs, my answer is going to be 1, 2. I look 1 to the right, so the 9 is going to go to a 0, rounds the 6 to a 7. So my answer is 4.70.